To finish off our discussion of pulsing networks, let's look at a particular example, a pulse width modulated network. Pulse width modulation is particularly useful because it can be used to control actuators, particularly motors. The idea is that when the pulses are short, the motor only gets a short shove and so turns slowly. When the pulse is long, it gets its supply for a longer time and turns quickly. In between pulses, the inertia of a rotor keeps the motor turning like a flywheel. Obviously, if you can train a network to produce such cycles, then you can use the output directly to control actuators like motors by using a high-powered switch like a transistor to turn on and off the power to the motor. So we can set up the network to have any topology as we did before, and we can calculate the activation of each neuron using a leaky integrator. For example, for neuron A, the equation is shown below, where you'll remember S subscript A minus was the sum of A at the last time step, and alpha is a constant less than 1. We can normalize this figure to between 0 and 1 using a normal sigmoid squashing function, and then use this to set the pulse width for A as shown in our previous videos. Shown on the screen is a more in-depth algorithm for the control of neuron A. Here the pulse lasts for between 1 and 10 time steps. Local A clock 1 is the neuron's first local clock, which keeps track of the progress when the output is 1. Local A clock 2 keeps track of its progress through the whole 10 steps. Go A flag is 1 when the neuron is triggered and 0 when it is not. The neuron will complete its cycle before responding to the next activation, NA. OA is the neuron output. The error for the network output can be calculated as shown in the previous video, or simply from the speed of the motor, where the error is the required speed minus the actual speed, and this then used to train a network until the error is 0. Before leaving pulsing networks, it's worth just noting that the activation functions could also be radial basis functions or polynomial ones, as we discussed in previous videos. This allows us to start building up networks with real computational power, which will be very useful when we come to discuss evolutionary algorithms later.